Okay, good morning. 9 a.m. and we can continue. Yeah. So in the previous classes, we started introducing magnetism. So let me just remind you a couple of major points. First of all, in order to produce magnetic field, a charge must move, right? So only a moving charge can produce magnetic field. Of course, electric field can be produced by both charge moving or stationary, it doesn't matter. Then we decided to use a small permanent magnet, like a compass needle, as a probe system to detect magnetic fields, right? And then we also agreed that the north pole of the compass needle is going to give us direction of the magnetic field. Then after that, we introduced magnetic field lines, very similar to the idea of the electric field lines. And after that, we introduced Biot-Savart law, right? One of the fundamental equations which allows us to find magnetic field created by a wire with a current, right? Any wire. So now we know how we can find magnetic field using Biot-Savart law. Now let's compare with the world of electricity. What did we have back then to find electric field? You remember? So we had Coulomb's law in collaboration with the probe charge. We could use that to find electric field. And then we also had an integral law to find electric field. Gauss's law. Right, you remember we were imagining Gaussian surface and then integrated to find the electric field. So, and as I keep telling you, there are lots of similarities between the world of magnetism and the world of electricity. So if we have two ways of finding electric field, most likely there must be two ways of finding magnetic field. So far, we know only one way, using Biot-Savart law. So now it's time to introduce the second option, an alternative way of finding magnetic field, and that is Ampere's law. So it will have it is an integral it has an integration in that. So it's like an integral form of the law. Right? So today the major point, we need to introduce this Ampere's law. Oh, I need to press on my slides in order to flip them. Okay, so that's what I said. So in the world of electricity, we had Gauss's law and now Ampere's law. And this Ampere's law, it's the second equation in the set of Maxwell's equations. Closer to the end of the semester, we will list all those equations. And Gauss's law is number one. Ampere's law will be equation number two. Right? And again, it's a fundamental, universal. You should be able to apply this Ampere's law at any point of the universe, at any moment of time. Anyone can do it. Completely universal, no restrictions. So far, no one has found any restrictions. Right? Okay, so since it's fundamental, again, it cannot be derived. So we just need to present it and start discussing and applying it. Right? The same way we introduced Gauss's law. Okay, so I can say here, tada, this is the Ampere's law, right? It looks great, gorgeous, right? Elegant, or maybe ugly for you, who knows, right? So what do we have here? We have integral, and you see we have a circle in the middle. You remember what does that circle mean? It means that the code is 6187. I think it has enough contrast, right? Again, I switched to blue color because then I will switch to whiteboard, and white color on the whiteboard impossible to see. And then again, you start asking questions what is the code, right? So I switched to blue color. Or maybe I will make it slightly brighter. Okay, so circle in the middle of the integral means that it's an integration over something which is closed. In the Gauss's law, we had closed surfaces, right? This is a line integral, or integration over a line, right? So ds, it's an element of a line. And, all right, so it means that this is integral over a closed loop, closed line. Again, the key word closed, like in the Gauss's law, we had closed surface, now closed loop. For example, circle is a closed loop. But of course, it doesn't have to be circle. It can be any it can have any complicated shape, right? But the keyword, it must be closed. If the line is not closed, this law wouldn't work. If the loop didn't wasn't closed, then this law couldn't be used. And of course, since this loop is used in Ampere's law, we're going to call it an Amperian loop. Like in the Gauss's law, we used the term Gaussian surface. Now, Amperian loop. Then, inside of the integral, we have dot product or scalar product of the magnetic field, and it's dotted with ds, which is basically infinitesimally small section of the loop, right? ds. Okay, I'll probably keep this loop here. Okay, and on that side, we have our universal constant, mu naught permeability of free space, right? Our vacuum basically describes magnetic properties of a vacuum, and then enclosed current. Okay, I will say about enclosed current a few words in a few minutes. So first of all, this Amperian loop, closed loop, again, it's imagination, right? It doesn't mean that if you use some Amperian loop that there must be some real loop. No, you decide. Okay, I can say I'm imagining a loop over here, right? And do this integration. Right? It's the pure mathematical concept. So Amperian loop is an imaginary loop. Then, again, as I said, it must be a closed, right? Loop must be closed, and you can use any loop your soul desires. No restrictions, right? You can pick any loop and you will be correct. But of course, you know that very often, in order to solve the problem, you must be smart and pick the best possible loop so that you can use, for example, the symmetry of the problem. Yeah, you will be not wrong by choosing some loop which has a complicated shape. But with that complicated shape, you would never be able to solve the problem. All right. So on top of being correct, you must be smart and pick the best possible loop so that you can solve the problem. But of course, you have the freedom to choose any loop you want. Like similar words are used to describe Gauss's law. Then, okay, this I enclosed. So every time we will have to pick an Amperian loop, closed loop, right? And enclosed currents, this I in, right? So all currents physically embraced by the loop. So current can be here, 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 as long as it is within the Amperian loop. So we assume that this is our Amperian loop. Then we must count that current. If the current is outside of the loop, no. And then also distribution of currents doesn't matter. If, for example, we have current at the very center of the loop, or over here, contribution to this Ampere's law will be exactly the same. Or here, distribution of current within the loop doesn't matter. Right? The same with the Gauss's law. If we had a charge in the Gaussian surface, it doesn't matter where the charge was, right? Here, 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 as long as it is within the Gaussian surface. The same with current here. Right? Okay, so now let's look at some arbitrary example. After discussing in general, so let's assume that we have three currents. I1, current up, I2, down, and I3 again up. And every time, if you want to apply Ampere's law, you have to start with what? You have to pick an Amperian loop. The same we did applying Gauss's law, right? First step was all the time, pick a Gaussian surface. Here we have to pick an Amperian loop, because without that pick, we cannot integrate this, because this is an integration over a loop, over that line. And of course, you wouldn't be able to tell which currents are enclosed, because again, you need to know the loop which you want to use. Okay, so as the first step, let's assume that I pick this loop. Okay, my soul desires this loop. And of course, yeah, as I said, we're going to call it an Amperian loop. Then we're going to integrate. And of course, integration must be done in a certain direction. So let's say clockwise or counterclockwise, but it doesn't matter really, but you have to pick a direction. So let's assume that I want to integrate that way. You see here, this way, then that way. So if you look from the top, it will be, if you look from the top, it will be counterclockwise. Right? Counterclockwise. Okay, and so now again, let's try to understand the meaning of this integral. This integral is far from being trivial. It's actually calculus 3. And most of you did not have calculus 3, but at a certain point you will have. And you will learn diligently how to evaluate these integrals. But here, although we do have stuff from calculus 3, but you will see that we will be able to integrate this integral, take it without actually taking it. Again, using high school knowledge, like we did with the Gauss's law. In the Gauss's law, we did the same. Again, those integrals are far from being trivial. Okay, so then, anyway, so let's try to understand the meaning. So what is inside b dot ds? So for example, let's say I take this point on the loop, or this point on the loop. Right? Of course, at that point, there is a magnetic field, net magnetic field produced by all these three currents. Then, of course, we have, if you take ds, infinitesimally small section of the loop, right? Of course, it will be along the loop, along the direction which we picked. And if you take a dot product, of course, you will get some number. I don't know, 5. Right? So, first number. Then you go to the next small section, ds, over here. Of course, over that section, there will be another value of the magnetic field because magnetic field changes. And again, you can multiply this dot product. You can calculate the dot product, b dot ds. So it will be the second number, I don't know, 7. You can add it to the previous number, right? So then you move to the next ds. Again, there will be some magnetic field. Again, you take a dot product, add to the previous 2 numbers, and you keep. And if you keep moving this way all the way to the very beginning where you started, when you complete this loop, and if you add all those contributions, b dot ds, that's the meaning of this integral. Again, integration is just a fancy word for adding small contributions. Right? In this case, b dot ds. Right? So that's the meaning of the integral. And so now let's discuss again currents. Again, currents enclosed. In this case, only these 2 currents, I1 and I2, are physically within Amperian loop. So Amperian loop physically embraces these 2 currents, right? So we must count only these 2 currents. Right? I3 is not enclosed, is not inside, so just forget about that. We don't have to include it in our calculations. Right? Again, I'm talking about these are enclosed, of course, right? Then, but now, obviously, one current is up, the other one is down. So obviously, they cannot go into the equation with the same sign, right? Or one of them must be positive, one of them most likely must be negative. So how can we decide which current is positive, which current is negative? Again, using right-hand rule. And right-hand rule, basically number 2, applied in a slightly different way. You remember right-hand rule number 2? We used to find direction of the magnetic field lines. Outstretch your thumb in the direction of the current, and your curled fingers gives you direction of the magnetic field. Now we're going to apply it in a slightly different way. Which way? You see, we picked an Amperian loop, and that is the direction of the Amperian loop. So now we're going to apply a right-hand rule, so in the reverse direction. Now you curl your fingers in the direction of this travel, in the direction of integration, right? Along the Amperian loop. And your outstretched thumb gives you direction for a positive direction for a current. Okay, here, a few years ago when I was making these slides, right, so I couldn't find the better hand. So, but whenever, okay, Looks ugly, but it explains the rule. Right? So again, you just need to curl your fingers in the direction which you pick for the Amperean loop, right? For the integration, and then your outstretched thumb gives you a direction for a positive current direction. So that's how we can make a decision which current is positive. In this case, you see I1, it's up along the direction of the thumb. So I1 is positive, and of course I2 is negative. So as a result, we can write Ampere's law, the right-hand side of the Ampere's law, as mu naught, you see, mu naught times I1 minus I2. Again, I3 is not enclosed, so we can forget about that. Okay, so that's the Ampere's law. And at this point, we can say, yeah, it's universal, it's fundamental, it's great, it's good looking, right, gorgeous, whatever. Where is the trouble? What is not great about this law? From practical point of view, of course, right? So most of the time, we use this Ampere's law to find magnetic field, to find the value of the magnetic field, right? And where is the magnetic field? It is buried inside of the integral. Again, in order to find magnetic field, every time you have to extract it somehow from the sign of integration. The same problem we had with the Gauss's law, right? Again, I told you, right? So in the Gauss's law, since electric field is inside of the integral, again, in order to find electric field, you need to extract it. Here, the same problem. And of course, most of the time, this extraction can be very painful. Sometimes you have to do it numerically, right? Unless you have a nice symmetrical distribution of current. And of course, in this course, we're going to use only nice symmetrical distribution of current so that we can solve and find exact expressions for the magnetic field, right? But of course, in the real world, it's more complicated, right? Of course, most of the time you'll have to use some kind of numerical techniques to find magnetic field. But we're going to use problems with a high degree of symmetry. Okay, so after this, what's left? We just need to start looking at examples. Yeah, also was planning to mention at the beginning of the class, right? So the next week we're going to have the second midterm exam on Thursday, right? So we have two classes, right, on Tuesday and Thursday. So the exam is on Thursday. Again, like exam one, it will be during the class, right? Maybe most likely we will start earlier, right? Again, if you don't have any classes, again, you will upload to Gradescope. The scope of material, most likely Ampere's law will be also included, but I need to think, I need to sit and think what will be on the exam, but most likely Ampere's law will be on the exam. Then exam review session most likely will be tomorrow in the second half of the day, maybe like 4:30. Okay, I will send email to you about that. So the second midterm exam will be next week. Yeah, so now it's time for me to start writing on the whiteboard. So let me switch to the whiteboard. You remember we in the previous recitation classes we already used this expression, right? But we didn't derive it, and I told you that derivation of that expression mu naught I divided by 2 pi r using Biot-Savart law is kind of complicated. And I told you that in the class we will derive it easily, and this is the moment. So we're going to derive that expression for an infinitely long straight wire with current using Ampere's law. So now we have two ways of finding magnetic field: Biot-Savart law, Ampere's law. And in this problem, as I said, you can use Biot-Savart law, but of course integration will be complicated. Ampere's law, it's a piece of beauty to use here, right? Much easier. Right? All right. So we have wire with radius r, right? And current flows, let's assume this way. So it's basically out of the board, I can show it here with one dot. So this is our current out of the board. I don't want to draw more dots because we will have plenty of stuff on this picture, so I don't want to make it even worse. Right, so Ampere's law, let me just rewrite it quickly. So integral over the closed loop b dot ds equals to mu naught times I enclosed, right? And again, which step should we make first? Without that step, we wouldn't be able to move any further. So we need to pick an Amperean loop. Again, you have a freedom to pick any Amperean loop you want, right? But again, we have to be smart and we have to pick the best one so that we can solve the problem, right? So being correct is not enough, right? Being right. All right, and first, let's say I want to find in part A, let's say in part A, I want to find magnetic field outside of the wire, basically where, okay, let me put a question mark, for R larger or equal than R capital. So let's say I want to find magnetic field outside. And now, yeah, we need to pick an Amperean loop, right? Since we want to find magnetic field outside, an Amperean loop basically we use sort of like to probe magnetic field. So if we want to find magnetic field outside, of course, we need to position our probe loop, of course, outside where we want to find magnetic field, right? So, and again, you can use any loop. You can use, for example, elliptical loop or even more complicated shape. But of course, with that loop, with those loops, you would not be able to solve the problem. Or maybe you will be able, but you will suffer a lot. Who wants that, right? No one wants that. So as a result, we need to pick the best possible. And I guess I think you should be able to guess that the Amperean loop will be another circle, of course, centered on the wire. Centered on the wire. So let me draw my Amperean loop. Right. Okay, so that's my Amperean loop. Right. Okay, so now once we picked an Amperean loop, we need to start, of course, evaluating integral and counting currents enclosed, right? So let's start with that integral. Integral over the closed loop, again, b dot ds. Lots of similarities with Gauss's law, even steps, which I'm going to make in order to evaluate this integral will be very, very similar. There will be two major steps. First, I want to see what's the dot product. So I want to see on the picture where is B and where is ds, and then the next step we will see. So first of all, ds. Where is ds on my loop? Before I can draw ds, what else do I have to pick? Just now I realized, right, that I'm now it's actually the right time to say about that. Direction, right? I didn't choose the direction. I pick an Amperean loop, but we need to decide, are we integrating in the clockwise direction or counterclockwise direction, right? So which direction should be the best for us? Since we know direction of the current, it's out of the board, right? I want to keep that current positive in my Ampere's law, right? So let's pick direction of integration in such a way so that current is positive, right? That right-hand rule number 2, right? So if I pick, for example, my integration direction this way, clockwise, right? In that case, I apply my right-hand rule, then positive direction for the current will be into the board. And our current will be negative. Who wants to deal with negative? Of course, in this problem, it's still not a big deal. But anyway, if there is a chance of writing something with plus, of course, I will go most likely, and you will go most likely with plus, right? So let's pick an opposite direction. So if we pick a direction counterclockwise, right, for an integration on this Amperean loop, then I do this, I apply my right-hand rule, and my thumb points outward, giving me this current positive. So this will be my direction of integration, right? So in this case, current is positive. And so now I can draw ds. Right? Let me draw a few ds's. For example, I can draw it here, right? So let's say this is my ds. I can draw, for example, here. So this is ds, or maybe here also. Right. You see, steps are very similar to Gauss's law. Now, magnetic field. Books usually, and this book usually says something like this. Because of the cylindrical symmetry, it's obvious that the magnetic field must be tangential. But I usually try to justify it, right? So let me justify it here as well. So now over here, I will justify direction of the magnetic field. So let me write justification of B direction. Right. So I will draw a separate picture over here, and then we can erase it at any moment. Right. So let's assume that this is our, again, our wire with the current. This is the center. And let's say I want to find direction of the magnetic field at this point. Right. It's basically this wire. Right. And let me draw this line connecting the center and the question where we want to find direction of the magnetic field. And now let me pick a small piece of wire over here. Right. Just a completely small piece of wire or current, piece of current in this wire, piece of current in this wire, because we have uniform distribution of the current. So exactly the same current density everywhere. So of course I can take a small, infinitesimally small piece of current, right? And so I want to know its contribution to the magnetic field at that point. So you remember we used that, right? So if you have a piece of wire, if you have a wire with the current, of course magnetic field lines are like this, right? And direction of the magnetic field is tangent, right? Tangent, right? So let me draw for this piece of current, maybe let me use blue. Right, so this is blue. Okay, okay. I will draw one of these magnetic field lines. So it will be. So this is one of the magnetic field lines. Okay, it's slightly distorted, right? But this should be at the center of this blue circle, right? And magnetic field is tangent to this blue. Now let me, but of course, since we have a uniform distribution of current, of course I can find symmetrically positioned small piece of current over there. Again, symmetrically to this line. And of course I can draw a magnetic field line produced by this green. It will be something like this, right? Again, it's distorted, not close to the center. So now magnetic field produced by this green wire will be this. And now if I add them up, these two fields, I will get net magnetic field tangent to the circle centered on the wire, at the center of the wire. So that's how I usually try to justify the tangential direction of the magnetic field. Right. Okay, so now we can go back to our picture, and I can draw over here magnetic field B. Over here I can, just in a few spots, B, and this over here also B. Okay, now after getting directions of these two vectors, we can continue with our integral. Right? And I will open my explanation box again. So, and I can calculate b dot ds. Of course, we know what we know the meaning of the dot product, and we know how we can write it explicitly. B ds times cosine of which angle? B and ds, they are parallel to each other, right? So the angle between them is 0, right? Cosine 0 degrees. So we're getting just b ds, and let me close my explanation box. Right. So it's just basically the fact that b is parallel to ds. Okay, let me probably add below. So b is parallel to ds. Yeah, my explanation box looked ugly a little bit. I thought I would be able to squeeze it. All right, anyway, so let me continue it here. So now, instead of dot product of two vectors, we are going to get a product of two absolute values, two magnitudes, magnitude of b and magnitude of ds. So integral over the closed loop of an Amperian loop b ds. Again, so the major advantage, the advantage of the beauty of this first step, that we managed to get rid of vectors. Now, these are just magnitudes. And the second step, now we have to use the symmetry. Look, if you are, for example, sitting over here, right, measuring magnetic field strength, and of course you can see that a magnetic field is produced by what? By this distribution of current. But if you move yourself from this point, for example, over here, and the magnetic field is produced by basically exactly the same distribution of current, you wouldn't be able to see the difference here or there, because current is distributed in exactly the same way. Or you can move over here, right, still being on the Amperian loop. Again, distribution of current will be exactly the same. It means what? It means that the magnetic field strength, not the vector, right? Absolute value of the magnetic field must be the same on the Amperian loop. Of course, if you move away from the Amperian loop over here, right, farther away if you move, of course, magnetic field becomes weaker. If you move close, of course, magnetic field becomes stronger. But in our integral, we stay on the Amperian loop all the time, at the same distance from the center of the wire. As a result, at any point on the Amperian loop, magnetic field strength must be the same. So that's why we need to pick a nice loop, in this case, circular loop, so that we can utilize the symmetry of the problem. Right? Okay, so now the second step, I can write since B is constant on the Amperian loop. Sometimes students write uniform. No, it's not uniform. Uniform, it's if you have magnetic field, for example, over here, right, and it's exactly the same at any point, the same magnitude, the same direction, yeah, that will be uniform. This is magnetic field just constant on the Amperian loop, right? And since this is an integration over Amperian loop, basically in this integral, we stay on the Amperian loop. We don't step away from that. Right? So we are on the loop all the time. So as a result, if B is constant, right? So if this is constant, right? Of course, we can extract it. And this is the major spot. One of the most important spots. So now it's a point where we can extract magnetic field from the sign of integration. So now as a result, I can write, so B and integral over the closed loop ds. So magnetic field is extracted. And now, final, so what's the value of this integral? Again, it's still calculus 3. It's still a significant amount of integration must be done in order to calculate this. But we're going to use our high school knowledge. We all know the answer of this integral. So again, what's the meaning of ds of this integral? You just take small ds plus ds plus until you complete walking along this Amperean loop, adding all these small ds's. If you add all those ds's, of course, you will end up with circumference of this circle, which is 2 pi r. Okay, and now I realize I picked the Amperean loop, but I didn't say that it has a radius r small. Right? R small, some arbitrary radius r small. So, of course, it will be equal to 2 pi r. 2 pi r, just circumference of the, and be careful, not r capital, because on the exam I can see very often it's just these r's are all over the place, r small, r capital, sometimes it's just a big mess. No, careful, right? So in this case, since we're integrating over the Amperean loop, so this must be r small. So equals to b times 2 pi r. So that's the value of this integral. And of course, from the other side, according to Ampere's law, it must be equal to mu naught I enclosed. So that's our that's what we got out of Ampere's law. But it's not over. The problem we haven't solved the problem. Right now we have two unknowns, b, which we need to find eventually, and right now we don't know I enclosed. This is basically a variable, right? So now at this point, we need to find I enclosed. And again, very often students, just when I ask students at this point, so we need to find I enclosed, they just solve I enclosed, this equation for I enclosed, right? They just move mu naught to that side. It doesn't give us anything because b is not known. Now we need to find I enclosed using some other arguments, right? So in this case, let's find I enclosed. And I think you should be able to tell me what's the value of I enclosed. Basically, it's all current physically embraced by our Amperean loop. So our Amperean loop is outside, right? Let's say this is Amperean loop. And our current is over here. So the whole current is physically embraced. The whole current I is within our Amperean loop, right? And again, it doesn't matter where the current is as long as it is within the Amperean loop, counted in. And the total current I is uniformly distributed over this cross-sectional area, and the whole current I is within the Amperean loop. So in this case, finding I enclosed is trivial, so it's just I. So the total current so now we can just plug it instead of I enclosed, and we can get the answer. So b times 2 pi r equals to mu naught times I. Okay, so from here we're getting the answer. So b as a function of r equals mu naught times I divided by 2 pi r. And that's the formula which we used 2 recitation classes ago, right? And again, that's only correct when you are finding magnetic field outside. So when r is larger or equal than r capital. Using Biot-Savart law, getting this formula, of course, much more complicated. Of course, this should take, I don't know, a couple of minutes. Right? But since I'm trying to justify everything, of course, it took us longer. Okay, so now, what about magnetic field inside? Okay, I will erase this now. So, yeah, I will write B. So now we need to find B as a function of R inside. Inside where R is smaller or equal than R capital. Again, Ampere's law, right? Um, okay, let me again rewrite it quickly. So B dot ds mu naught I enclosed. And again, first of all, we need to pick a Gaussian surface. Oi, Gaussian. I'm still switching. My brain is still switching from the electricity to magnetism. Amperean loop. And since it's the first class I'm introducing Ampere's law, I'm still comparing it quite often with the Gauss's law. So. Okay, so now we're interested in the magnetic field inside. Then, of course, our Amperean loop must be in that region, must be inside. And again, you can pick any loop you want, but of course, we need to be smart and pick the best possible so that we can use the symmetry of the problem, right? And we need to pick Amperean loop. The circle will be an Amperean loop, but of course positioned inside of some arbitrary radius r. So this will be my Amperean loop now. Right. And then, guys, these steps up to this point will be exactly the same over here. Not a single symbol different. Exactly the same. I can, of course, I can pick exactly the same direction for ds. Let's say this is my ds, right? So this is ds. Then, of course, magnetic field direction will be still the same with the same justification. So this b, this is b, right? So all these speculations exactly the same up to this point. So similar to part A, we can write, so the integral of this b dot ds, it's actually not similar, it's exactly the same. So you will get b times 2 pi r. But of course now r is less than r capital, that's the only difference, right? And from the other side, it must be equal to mu naught times I enclosed. So that's what we have. And now we need to find enclosed current in order to find the expression for B. Right. And usually first, I prefer to see on the picture where this I enclosed is, right? Again, it's a current physically embraced by our Amperean loop. Amperean loop now is here, now inside, right, for this part of the problem. And so our enclosed current is this. This current is physically embraced by the Amperean loop. You see? I highlighted. So that's where current I enclosed current is. Of course, it will be smaller than I, because this current I is uniformly distributed over the whole cross-sectional area of the wire. But now our I enclosed is in a smaller cross-sectional area. So now we need to find that. So, in order to find that, of course, you remember the definition of current density. J equals I divided by A. So basically, current density, you need to take, in order to find current density, you need to take current and divided it by the cross-sectional area over which that current is distributed. Right. So now let's first find current density in this wire. Right. So let me write, so first I in, right, and J, current density. What can be used to find current density? Total current I. Right? Total current I is uniformly distributed over this cross-sectional area with radius r. So we can take total current I and divide it by pi r capital squared. I divided by pi r capital squared. So that's current density. Then, using current density, can you find now I enclosed? Again, look at the formula. So now if you want to find current, you need to take current density and multiply it by the area through which I enclosed is flowing. Right. So current density we just found, and we need to multiply it by the cross-sectional area where our I enclosed is. So by this cross-sectional area which is highlighted. So I enclosed will be equal to what? J times pi r small squared. Plug J in, so we'll get I divided by pi capital R squared times pi R small squared. Pi gets cancelled, and we have the amount of enclosed current. Right. So that's how we usually explain. Sometimes, right? So that's the value of I enclosed. Sometimes, some students find this explanation better. Or let me write or. It's an alternative way of finding I enclosed. So this is one way of finding current density. J equals I divided by pi r squared. How else can you find current density? We can use our enclosed current, which we need to find. But we know that I enclosed goes through this cross-sectional area. So we can also write current density equals to I enclosed divided by pi r squared. Since current is distributed uniformly, this density, current density, and that current density must be the same. So this equals to that, and you will get I enclosed. Right? So I divided by pi r squared equals to I enclosed divided by pi r small squared. And from there, you will get exactly the same formula for the enclosed current. So I just noticed when some students had troubles understanding this logic, although it's reasonably simple. But once I showed this way, we can find current density this way or that way, compare them, and you will get I enclosed. Okay? The review session, right? I will send email, so most likely it will be tomorrow in the second half of the day, around 4:35. I need to sit and think through when exactly. So tomorrow, and of course we're going to have a. It will be in the we'll go to the class, right? And okay, I will send email with all the explanations. Right. So back to the problem. So now we found I enclosed. Right, and we can just plug it in our Ampere's law and find the expression. So now let me rewrite this. B times 2 pi r equals to mu naught times I enclosed, which is I times r squared small divided by r capital squared. So something can be cancelled. Pi is not cancelling. All right, so only one r can be cancelled. And from here, we're getting the formula B as a function of r equals mu naught I. 2 pi goes in the denominator with r squared. 2 pi r squared and times r. So first I collected all these constants, and r is our variable. So when we are when we are inside, right, measuring magnetic field grows linearly with radius. Right. So let me frame it. Right, and let me remind you that this is for r small less or equal than r capital. Let me just quickly plot B versus r. So now if we plot, and we will call it today, B versus radius. And let's say this is the radius of the wire, r capital. So when you are inside, magnetic field grows linearly. So it will be, let's say this is maximum, something like this, straight line. And outside, mu naught I 2 pi constants, but variable is downstairs, so 1 over r. So it will decay as 1 over r. So here, b is proportional to r. Here it's proportional to 1 over r. Okay, so application of Ampere's law. In your recitation classes, you will solve a more complicated example when there is a hole inside, right? So I will do it in my sections on Monday.